What do you remember about Schrödinger's cat? In 1935, physicist Erwin Schrödinger created what would become one of the most significant thought experiments in scientific history. Before exploring this concept, it's important to note that no actual cats were involved in this scientific work. This was purely a thought experiment, a tool scientists use to explore concepts using logic and imagination. A thought experiment is a mental exercise scientists use to understand complex ideas. Consider Einstein imagining riding on a light beam to understand relativity, or Galileo contemplating objects falling from the Leaning Tower of Pisa. These mental scenarios help scientists develop and test their theories before conducting physical experiments. Schrödinger's thought experiment involves a sealed box. The box must be completely sealed because in quantum physics, observation changes the behavior of quantum systems. This is known as the observer effect. Much like how using a thermometer to measure the temperature of a small cup of water changes the water's temperature slightly, measuring quantum particles alters their behavior. This occurs because at the quantum level, any measurement requires interaction with the system, and this interaction creates changes. Inside this theoretical box sits an imaginary cat, along with a specific setup, a radioactive atom that may or may not decay. The atom's behavior is similar to a random event, like popcorn kernels popping in a microwave. While we know each kernel will eventually pop, the exact moment remains unpredictable. The box also contains a Geiger counter to detect atomic decay. Scientists refer to this atomic change as decay, though it differs from typical decay. The process more closely resembles transformation, where the atom changes form and releases energy. According to quantum mechanics, until someone opens the box and observes the system, the radioactive atom exists in both states simultaneously, both decayed and not decayed. This means theoretically the cat would be both alive and not alive at the same time. This was precisely Schrödinger's point. While quantum mechanics suggests that tiny particles can exist in multiple states until observed, applying this same logic to a larger system like a cat demonstrates the apparent absurdity of these quantum rules when applied to everyday objects. Today, scientists at the University of New South Wales have transformed this theoretical concept into practical application. Using an atom of antimony, they've created a quantum system that exists in 8 different states simultaneously. Unlike traditional quantum bits or qubits that operate in 2 states, antimony's nuclear spin provides more possibilities. The antimony system demonstrates remarkable stability. As researcher Shi Yu explains, the system maintains integrity even when small errors occur, similar to how a cat with 9 lives remains resilient to minor setbacks. This stability represents a significant advance in quantum computing. Dr. Danielle Holmes and her team have implemented this system in silicon chips, the same material used in conventional electronics. This compatibility with existing manufacturing processes suggests potential for mass production of quantum computing components. The breakthrough addresses a fundamental challenge in quantum computing error correction. Traditional quantum systems are highly susceptible to interference, but antimony's expanded state space provides greater stability and error tolerance. This development could impact various fields, from cryptography to molecular modeling. These more stable quantum computers could process complex calculations that would take conventional computers millions of years to complete. The project represents international collaboration, including teams from UNSW Sydney, the University of Melbourne, Sandia National Laboratories, NASA Ames, and the University of Calgary. Through their work, Schrödinger's thought experiment has evolved from a theoretical critique into a foundation for advancing quantum computing technology. What began as a scientist's theoretical challenge to quantum mechanics has become instrumental in developing next-generation computing systems. This progression demonstrates how theoretical physics can lead to practical technological advances. For more on this story, find a link to the article on Earth.com in the description.